How we doing? Yeah, windowless room in the afternoon, right? Everybody loves it. A lot of smiling faces right now. But I promise we'll get through it. My name is Deshard Joyce. I'm an assistant professor at the City College of New York, and I'm so excited to be here today to tell you about our work, society, practical cryptography in smart home contexts. So let's get started. Suppose a user wants to log into an online service. These days it's going to involve some form of two-factor authentication, hopefully. You're going to have a mobile device with an app, it generates some codes, you're going to send that to the service for a connection, maybe along with the password. Why does this work? We have some cryptography. Both the mobile device and the online service have the same shared key. Now, there's an issue with this, and it's that mobile devices are mobile. What happens if you lose your device? And we've seen this in the research literature and in real-life anecdotes. Your keys get extracted off your phone, basically no matter what you do. And this can be done by people who steal your phone. And it can also be done at the border, for example, by law enforcement agencies in many countries. And this is actually exactly the reason why my dad doesn't use online banking. It's because he's worried that people are going to take his keys, generate the same codes, connect to his bank account, and drain all his funds. And it's fun to talk about my dad, but you can also think about a much more serious scenario where we're talking about a journalist, right? And this has been brought up in this session, many sessions throughout this conference, where you have a journalist with some kind of secret information on an online service, then authentication becomes like the most important thing. So one idea here is, okay, let's take the mobile out of the device. What if we keep our secrets somewhere else? If we keep them somewhere else, somewhere that we consider to be secure, we're less likely to use them. It's a form of kind of opt-in misuse resistance, so that you can feel more safe when you use your online tech. So that is our goal here. We're going to have our user, when we're inside their house with their phone or some other secure context, they're going to be able to access their services. So what about adversaries? Well, we talked about the compelled decryption adversary, right? If someone tries to extract your keys from your phone, we want to make sure you can access the service. And as well, now that we have this kind of secure area, the secure context, we want to make sure that any person with local network control over the context can't also access services. So this is what we're going to address in this solution. Okay, so let's try to build a solution here. We have an online service. We have this cryptographic secret. That's what's going to be used for this 2FA. Where do we put the secret? Well, we have our mobile device in the home. A lot of you are probably screaming internally, put it in an HSM, right? And this is not a terrible idea, because you are indeed keeping the secret at home. You can query the device for the codes that you want and forward it to the service. And this is great, because now we're keeping the secrets at home. But there is cost involved with this, right? There's a monetary cost, because these HSMs can get kind of pricey. And there's like a mental cost, because now you have to manage an HSM, and it's not exactly something you can configure on your first try. So we need something a little better. Well, users now have their own hardware, not just desktops and laptops, but also things like smart fridges, for God knows why. And we talked about how smart homes are terrible privacy, invasive things, and yet people still buy more of these. So we have a smart home of several devices that provide some functionality. They're fixed in place. So what if we took our cryptographic secret, broke it up into little shares, put them on all the devices, and had these devices work together to provide the codes to connect? So what if we could do this? How can we potentially do this? Let's take a look. And to do that, we're going to have to enter the crypto zone. And don't worry, I mean cryptography here. We're going to talk about pseudorandom functions. So a pseudorandom function is a cryptographic primitive that accepts some input. It's parameterized by some key. You get an output. The security model of a PRF is that without this key, the output is indistinguishable from random values. And this is exactly how you build two-factor authentication. The input is just the timestamp, the current timestamp, and you generate this output, this random-looking code, that both the phone and the server can validate. So let me introduce a different model here, the threshold distributed PRF. So we still have the same input. We're going to input this thing. But now we have this TD-PRF algorithm. And this algorithm takes a share of the key, basically some part of it. And this share of the key, when you output to this other value called, or excuse me, other algorithm called recombine, you can take these partial outputs and recombine it into the actual output. When I say actual output, I mean this. The pseudorandom function output on the left will be the same as the pseudorandom function output on the right. So this is a distributed system now because now we have multiple parties working together, but it's also a threshold system because only t out of n parties are required. Here we have 3 out of 3, but you can imagine if you had like 10 devices, maybe you only want 6 of them to return a value. And this helps with like efficiency in practical terms. Okay, so we have this TD-PRF thing, and it will provide the cryptographic service that we need while federating trust amongst these devices that we want to reuse. So this is the core of our system, which we call SocIoTy. So what is the setup for SocIoTy? We have our online service, and we're going to define 2 cryptographic secrets for reasons that will become clear in a moment. The user is going to download both of these cryptographic secrets. And we're going to call the first one the smart home key. And we're going to take the smart home key, break it up into little shares, and put them on each of the devices. Once that's done, we are going to securely delete the smart home key off of the phone. Then we have the other cryptographic secret, which we're going to leave on the phone. We'll call it the phone key. So the smart home key is in the smart home. The phone key is on the phone. Pretty simple. So now how do we actually generate the codes? Well, when you are inside of your secure context with this phone, you're going to request for the current timestamp some evaluation. And you're going to request on this TD-PRF. What's going to happen is that each IoT device is going to perform this partial evaluation on the timestamp with its share of the smart home key. So the fridge will return value A, the speaker, value B, the camera, value C. All of these are put together and returned to the phone. So that phone has values A, B, C, and can compute this recombine algorithm, which returns some value X. And remember, X is the same value as if we used a regular PRF algorithm on the whole key. Okay? So we basically have a PRF evaluation already, but we're not going to be done yet. We are also going to evaluate the PRF on the phone key, Y. And we have that on the phone in its full form. And then we're going to do X plus Y mod 10 to the 6, which is going to give us some 6-digit code that we can forward to the service. So what do we do here at the end? I don't mean to pull a fast one, but we combine the outputs of 2 PRFs. And why would we do this? Well, to understand why, we have to look at the security model. Because we talked about, just now, if we're in the smart home context with our phone, we can access the service by computing X plus Y mod 10 to the 6. This is what we want. But what about our adversary? So our local network adversary, who has control of the smart home, potentially, the entire smart home, what can they compute? Well, they can compute all of these intermediate values. They can even compute the recombined value, but they don't have the phone key. So they can't actually compute X plus Y mod 10 to the 6, which is what you need on the server. And similarly, if you are a compelled decryption adversary, you have access to the phone, so go nuts. Compute Y equals the PRF evaluation on the phone key. But you don't have access to the smart home, so you can't compute X. That way, you can't access the server either. So we basically defended against this threat model by using this kind of dual-layered PRF. It gives us the security we need to defend against this threat model. So how do we evaluate this? Well, we run an app. It kind of looks like a regular authenticator app. And we set up a simulated smart home of 17 devices. So we had some Raspberry Pis of different flavors. We also had tiny little SP32 microcontrollers that my co-author Logan spent a lot of time wrangling. So good props to him. So what we did is we ran this protocol using this app. It generated codes by asking all of the devices for partial evaluations, performing the recombine, and all the processes I just said. So here is a chart of the end-to-end results. You can see here that for t equals 9, which means we're waiting for 9 devices to respond, takes 0.2 seconds. For t equals 17, which means every single node needs to respond, it takes 0.4 seconds, higher spread because when you're waiting for every device, sometimes a really slow device will slow everything else down. But this is actually pretty good. Everything's under 1 second. And if you think about it, the animation for this circle takes about a second, so you can kind of fake out a user by just like showing an animation. Simple trick in the old books. So this is clearly actually practical, dare I say. And that is our system, SocIoTy. It provides the at-home cryptographic services you need while reusing the existing hardware that users have, at the same time federating trust across that hardware. And it's efficient in implementation. And our solution is designed so someday everyone can say, we live in a society. I'm Tushar, here's my email, my website, follow me on the app formerly known as Twitter. Please take a look at our paper and artifact, QR code available. I'm happy to take your questions. Thank you for your time.
Hi, very nice talk. And this all sounds really cool, except I was thinking about like the thing you were talking about at the beginning where you're talking about the reasons why you can't just have a hardware store, and it's like because you have to buy the thing and then manage it. And then I was trying to imagine like having all these random IoT devices and trying to get my shares on them and trying to get them to speak this protocol and like thinking that that would be more usable, and I'm trying to figure out what the vision is for that.
Yeah, this is actually a fantastic question, and my answer to you is undergrads. I have some undergrads working on implementing this using, I'm serious, implementing this using actual, huh?
You put the undergrads in the fridge?
Yeah, no, we're not fridging the undergrads. As much as I know some of you in the audience want to. But actually what we're doing is we're trying to implement this using like JavaScript and stuff like that, using the native IoT protocols. So then we can just put it on the IoT app stores. And actually now like IoT app stores are becoming more complex and allowing more scripting. So we are hopeful that this can actually be deployed without vendor intervention. But if you're a vendor and you're like, that's wrong, please come talk to me, because I want to avoid like spending a lot of time on that. But that is kind of our vision, is trying to move forward by deploying this on the existing systems. We have to use Raspberry Pis as a stopgap just for evaluation, just to test things. But we actually do foresee that if we can install this on app stores, we can go ahead with it.
Hi, here.
Yes, hi.
Very cool idea, I really like it. I was looking at your threat model and you were assuming that an adversary that has access to the local network might be able to access the secret pieces of the key that you're sharing, right? But I was thinking, most of us connect our phones also to our local network, right?
Yeah.
So in that case, wouldn't the adversary also get access to the key on your phone?
Yeah, and we talk about this a little bit in the paper, but a lot of the remote style attacks without physical access, easier to do on IoT devices based on the literature, harder to do on phones. I'm not saying it's impossible, but it is harder. So I'm not going to say this is the end-all be-all solution, and if you're under a nation-state attack, you should use this. But the idea is this is an upgrade for security for people like my dad who aren't going to be able to do like crazy HSM stuff, but still want to feel a little bit safer when they're using stuff online.
Thank you.
Hello, thanks for the great talk. I had a question about how you view this working in cases where like one of your smart devices maybe like is in the middle of an update or it like fails. Or maybe if you're like out of the house and suddenly the power goes out in your house, do you have like mechanisms to overcome that, or how were you thinking about it?
Yeah, this is a good question. Actually, when we started this work, we tried to look at MPC and some dynamic forms of MPC that allow stuff like that to happen. If something fails, can you hand off state? It turned out that that stuff was a little too slow on IoT devices right now. But I think that model is very interesting, especially considering the whole planned obsolescence model of offenders these days. I don't have an answer for you right now, but I definitely think that's a model we should look at if we're trying to get this more out there.
I have two questions. One is, can't you use like MAC addresses of the devices near your phone? Just scan for them, and that would be the shares of the key. Right? So you don't need actually for devices to do anything. You just collect this, make it a share. And the second question, in your technique, do you need the server to use a different PRF than the server already uses? In other words, existing services, they have a specific PRF. You can implement it inside NPC, but my guess is that you're not doing that. You're doing something else, so you would require the server to also update how what it
Yes. So the answer to your first question is yes. If you just printed out all the shares, the QR codes, or put them on the devices, you could reconstruct it and compute this. But to me, that feels more like a backup solution rather than an ongoing solution, allowing folks to not have to reconstruct the key in case, for some reason, they don't want it ever on their phone, or because it's a little bit more convenient to not have to like go around the house and scan it. We talk a little bit more about this in our paper in terms of like the physical implementation. Your second question, which is about implementation, yes. So it does require that the server change their PRF implementation. We are working with the unnamed undergrads to try to implement the same standard that is used for 2FA right now. I don't remember it off the top of my head, but Google has a standard for 2FA, like defining algorithms. So we're hoping that with that, it's more of a plug-and-play type solution. But you're right that we can't just re-implement, HMAC or whatever inside of this.
I think we need to move on.
Thanks for your talk. We
Yeah.
enjoyed it.
Thanks, y'all.